Hello everyone. This is the second part of chapter 3 where we are going to discuss the non-ideal diodes. In the previous video we discussed the ideal diodes where it had two regions of operation. The forward bias, which is on, and the reverse bias, which we represented as off. When the diode was on, the diode was replaced with a short circuit, and when the diode was off, it was represented by an open circuit. Okay. In this video, we are going to discuss the non-ideal diodes, which consist of three regions of operation, which are the forward, the reverse, and the breakdown region. Now, forward bias region occurs when the voltage across the diode is greater than 0, and reverse bias occurs when V is less than 0. Whereas the breakdown region occurs when V is less than minus VZK. Now what is VZK? Z stands for Zener, which we will discuss later on. It stands for Zener. And K stands for Ni. Why did they call it Ni? I will show you in the graphical interface of the IV characteristic. This is the IV characteristic of the non-ideal diodes. For the ideal diode, it was like this. IV, it was as follows. This is the IV characteristic of an ideal diode. Now for the non-ideal diode, as you can see that this line was shifted to the right, and now its value is 0.7. What is this value? This is the default value for a non-ideal diode, which is the voltage drop across the diode if it's on. Okay. If V is greater than VD, the diode will be forward, which is on. If it's less than VD or 0, it will be reverse bias. And if the voltage across the diode is less than minus VZK, then we are in the breakdown region. Now they called it Ni because if you notice that this is someone sitting, and when you reach this point, it's a Ni. This is similar to a Ni. Okay. Now, as I said, if V is greater than VD, greater than 0.7, or let's say 0, then the diode will be on. Greater than 0, the diode will be on, and we will represent it as a voltage source, a DC voltage source, and its value is 0.7. And if V is less than 0, then the diode is off, which is a open circuit. When V is less than minus VZK, then we are in the breakdown region, meaning the diode is no longer working. It's completely destroyed. Okay? Moving on. Now, when analyzing the forward bias region, there's an approximation for the IV characteristic. For the forward bias region, the behavior is approximated as follows. ID equal to IS E VD over VT. This is to be memorized. ID is the current across the diode. IS is the saturation current, which comes from the manufacturer. VT is the thermal voltage, which is equivalent to 25 millivolt at room temperature. VD is the voltage drop across the diode. Okay. Now, if they ask us to find ID, then this is the equation. Whereas if they asked us to find VD, then we have to make it the subject of the formula. If ID is equal to IS EVD over VT, then EVD over VT is equal to ID over IS then Vd over Vt is equal to ln of Id divided by saturation current, then Vd is equal to Vt mod ln Id divided by Is. Okay. Now, if they asked us to find Is, which is the saturation current, it's simple. You divide Id by the exponent. There's a way to know if our answer for the saturation current is correct or incorrect, through its power. Now, the saturation current usually it's very small. It has a very small power. Its range is from generally it's from minus, let's say 13, minus 14, 10 minus 15, or 10 minus 16. If it's in this range, then it's correct. This equation is used to find the requirements for only one diode. Okay, I will explain this further later on. This equation is used to find requirements for one diode only. Okay. If we are analyzing the operation of the diode using forward bias region, then there are three ways of analysis. The first and the most accurate one is the exponential. So here we're saying that there are three ways to analyze the operation of a non-ideal diode. And its forward bias region. Operation of a non-ideal diode in its forward bias region. The first and the most accurate is the exponential model. It's the most accurate and it's an iterative model. It's iterative. The second one, and it's the most commonly used and it's the simplest, is the constant voltage drop model. The third and the last is the small signal model, where there is an AC component superimposed on the DC component. Okay, let's begin with the exponential model. Now, if we are analyzing the circuit using the exponential model, let's say we have a voltage source, resistance, and a diode. Okay, and you were asked to find I across the diode and the voltage across the diode. Now, in order to find ID, it will be Ohm's law, VDD minus VD divided by the resistance. But if we were asked to find the voltage drop across the diode, then there are two ways. It's VD equal to VT ln ID over IS, or VD2 equal to VD1 plus VT ln ID2 over ID1. I recommend using this equation because we are going to use it for the entire chapter. So instead of learning two methods, it's better to use this one, okay, rather than this. I will show you both, and I will explain why I will explain why I'm recommending the second one. And how did I get this? I will show it to you in a moment. Okay. If we have, for the same circuit here, let's say VDD is equal to 5, VD equal to 0.7 volt at ID equal to 1 milliampere, and resistance is, this is VD, and resistance is 1 kilo ohm. Okay, we were asked to find VD using exponential model. Two iterations is required. Now every iteration that you do will give you a more accurate answer. Two iterations is required. Okay. How do we start? We start with the first iteration, obviously. Iteration number 1. For every iteration you will need to find I and V. Okay. So ID1 is equal to VDD minus VD over R. VDD is 5. Okay. VD is 0.7 divided by R, which is 1 kilo ohm. Now make sure that you differentiate between this VD and this VD. They are not the same. Okay. This VD is the default VD, the voltage drop across the diode, whereas this VD is the sample VD for calculating IS. This is the sample. How can you differentiate between the sample and the regular VD? Through the keyword at. This is the keyword. If you see at, voltage at current, then this is a sample for calculating IS. Okay. Now, ID is equal to 4.3 milli. Now we need to find VD. VD1. VD1 is equal to what? It's equal to VT ln ID1 divided by IS. Okay. We already know what's VT. It's 25 millivolt ln ID1. We just found it out. It's 4.3 milli. And IS we do not have. We need to calculate it through the sample. Now how do you calculate a sample? Sorry, how do you calculate an IS? IS can be calculated using this equation. Sorry. ID equal to VT. No, sorry, it's IS. ID is equal to IS. I'm getting confused here. VD over VT. Okay. Now IS is equal to what? It's ID divided by EVD over VT. ID is equal to 1 milli, because here we're finding the IS. VD is 0.7. Now we're taking this value divided by what? Divided by 25 milli. This will give us 6.91 times 10 to the power of minus 16. Take note of the power. Look at how small it is. Okay, so this is IS. After finding IS, I can plug it in here. 6.91 times 10 minus 16, and it will give me the first voltage drop across the diode. It will be 0.7365 volt. I recommend that you put at least 4 decimal points so that your answer becomes more accurate in the second iteration. If you put only 2 decimal points, then in the second iteration you will get almost the same answer. So now let's move on to iteration number 2. For iteration number 2, we need to find again ID 2, which is VDD minus VD1 divided by resistance. So it will be 5 minus 0.7365 divided by 1K. This will give us 4.2635 milliampere. Okay. Now finding VD2, it will be equal to VT ln ID2 divided by ID1. ID2 divided by ID1. So divided by IS, sorry. Divided by IS. VT is again 25 milli. Then ID2 is equal to 4.2635 milli divided by 6.91 times 10 minus 16. This will give us 0.7363 volt. As you can note here that when we started with VD, the default VD, it was 0.7. The default is 0.7. But when you use the exponential model, you ended up with 0.7363, which is more accurate. Now, the another solution which I recommend is the other solution. Let's begin again with ID1. ID1 is the same. It's VDD minus VD over resistance. VD is the default, so it will be 5 minus 0.7 divided by R divided by 1K. This will give us 4.3 milliampere. Nothing changed so far. Now, when you want to find VD, okay, we'll use ID equal to IS EVD over VT. Now, instead of going onto the side, finding IS and then plug it into the equation, we will divide by the same equation to cancel IS. Okay? The numerator, so IS here will be cancelled. The numerator will be the current iteration, which is iteration now, and the denominator will be the previous iteration. Okay? So as we are in iteration number 1, this is iteration number 1. As we are in iteration number 1, here we will say ID1 and VD1. And in the previous iteration, it will be 0, right? So 0 is equivalent to IS and VDS. IDS and VDS is the sample. IDS, VDS. Okay? Now, we're trying to find here VD1, right? So if you want to make this the subject of the formula, it will be ID1 divided by IDS equal to exponential VD1 minus VDS divided by VT. Because here powers, when we divide powers, they will be subtracted from each other. And because VT and VT, they have a common denominator, then we are subtracting the numerators. Okay. Now, doing the natural log, applying the natural log will give us the following. So VD1 is equal to what? VD2. This is VDS, right? This is supposed to be VDS. VDS plus VT ln ID1 divided by IDS. This equation is exactly the same as the equation I showed here. This is the new iteration. This is the old. This is a new. And this is old. Okay? Here. This is a new. This is old. New and old. Okay? Let's plug in numbers now. So VDS, we said it's 0.7 plus 25 milli ln ID1 was 4.3 milli, here 4.3 milli, divided by IDS. IDS was 1 milliampere. Okay, plugging this in the calculator will give you 0.7365 volt, which is the same as the previous solution. Okay, now we found VD1. We're done with the first iteration. Let's move on to the second iteration. Iteration number 2. Finding ID2 is equal to VDD minus VD1 divided by resistance. VDD is 5 minus 0.7365 divided by 1K will result in 4.26335 milliampere. Okay, finding now VD2 it's equal to what? Let's use directly this equation. The old iteration now is VD1, okay, plus VT ln ID2 divided by ID1, new versus old. So VD1 is equal to 0.7365 plus 25 milli ln ID2 is 4.2635 milli over 4.3 milli. This will result in 0.733 volt. Okay, now moving on, this is the exponential model. Moving on to the constant drop model, constant voltage drop model. It's the simplest model. Why? Because it says that the voltage drop across the diode is 0.7 and it satisfies me. You do not have to find a more accurate answer. So if we take the same example as before, VDD, resistance 1K, this is VD and this is ID. The question says find ID and VD using the constant drop model. Okay, now we already know that VDD is equal to 5 volt, VD is equal to 0.7 at ID equal to 1 milliampere, and R is equal to 1 kilo ohm. As here you have an at, this is a sample and we have to use it only for calculating IS. What's ID now here? ID is equal to what? It's Ohm's law, right? VDD minus VD over R. What is VD? We said that we are in the constant drop model, and the constant drop model says that the default value, which is 0.7, it satisfies me. So this is the default value of VD. Make sure or make note that this is not this, right? They're not the same. This is for the sample for IS and this is the default. Okay. So here it will be 5 minus 0.7 divided by 1K. This will result in 4.3 milliampere. Okay. Great. Let's take another example. Okay. Here we are having the VDD resistance. This is VD, and here we are having ID. Okay. VDD is equal to 5 volt. R is equal to 10 kilo ohm. VD is equal to 0.8 volt, at ID is equal to 1 milliampere, okay, and VD is equal to 0.7 volt, okay, or let you know what, let's change this to 0.9, and this is 0.8. Okay, the question says find VD using exponential model, and 2 iterations is required. The first step is to find, no, this is part A, and for part B, find VD using constant voltage drop model. Okay, so for the first part, we need to start with the iteration number one. For the first iteration, we need to find ID1. Now ID1 is equal to VDD minus VD divided by R. VDD is 5, VD is 0.9, because it's not the sample, but it's the default value, but the professor or the instructor have changed the default value, and now it's 0.9. This is the sample, because it has an at. Okay, so it's 5 minus 0.9 divided by 1K, and this will result in 4.1 milliampere. Finding VD1, it's equal to VDS, previous iteration, plus VT ln ID1 divided by IDS. Okay, now VDS is equal to what? It's equal to 0.8 plus 25 milli ln ID1 is 4.1 milliampere divided by IDS. IDS is 1 milliampere. Okay, this will give us, I did not calculate it previously, so I'm doing it right now, plus 0.8. This will give us 0.8353 volt. Okay, now what is, let's do the same thing for iteration number 2. For iteration number 2, ID2 is equal to what? It's equal to VDD minus VD1 divided by R. So it will be 5 minus 0.8353 divided by 1K. 5 minus answer divided by 1K is equal to 4.165. Let's put it as 47 milliampere. Okay, now finding VD2, it's equal to VD1 plus VT ln ID2 divided by ID1. VD1 is equal to 0.8353 plus 25 milli ln ID2, which is 4.1647 milli divided by 4.1 milli. Okay, divided by 4.1 milli ln answer multiplied by 25 milli plus 0.8353. Okay, this will give us 0.8357 volt. Okay, I hope it's clear now. This is the exponential model. Now for the constant drop model, what is VD? VD is 0.9, and for ID, it's equal to VDD minus VD divided by R. So it will be 5 minus 0.9 divided by 1K, which is equal to 4.1 milliampere. Okay, moving on to the next question. Let's say we have this circuit. We have here 10 volt R resistance, and we have 3 diodes. And the question says design. Here it's V output. We're having VD equal to 0.7 volt at ID equal to 1 milliampere. VO is, this is VD and this is VO. VO is equal to 2.4 volt. Okay, and the question says design. Now whenever they say design, then we have to find R. Okay, if the question says find R, then you have to think Ohm's law directly. Think Ohm's law. Now R is equal to what? It's equal to 10 minus V naught divided by I. What is the relationship between I and ID? They are equal, right? Because there's no use of this. It's just a pointer. So I is equal to ID. And how do we calculate ID? Through this equation. IS E VD over VT. Okay? Now every time, whenever you have IS, try to cancel it out. How? By dividing by the same equation. And the denominator is the old, and the numerator is new, which is the current now, values right now. And the denominator is the values earlier or in the previous part. So this is a new and this is old. Okay, now IS and IS, they cancel each other out, and we said this is new, old, and old. We're trying to find the current right now, so we are trying to find ID new equal to ID old exponential VD new minus VD old divided by VT. Okay, old is what? We do not have a previous part in the question, so it will be the sample. So ID old is 1 milli exponential VD new minus VD old. VD old is what? It's 0.7 from the sample divided by 25 milli. Now what is VD new? What's the voltage drop across the diode? As you can see here, now of course it's not the default value. Why? Because the professor or the instructor have given us the value in an indirect way. As you can see here, we were given V output. What is V output? It's the overall drop, voltage drop across all the diodes. So what is the voltage drop across only one? So this is VD, this is VD, this is VD. Okay. So VD, voltage drop across one diode, is the voltage drop across all diodes, the overall, this is VD, divided by the number of diodes. So it will be 2.4 divided by 3, which is equal to 0.8 volt. So as you can see here, the default value is, or the voltage drop across the diode is no longer the default value, which is 0.7. Okay, it's 0.8. So 0.8 minus 0.7 over 25 milli. This will give us 54.6 milliampere. 6 milliampere. And here V output is 2.4 divided by 54.6 milli. This will give us 139 ohm. Okay. Now, there are several ways to be provided with VD. The first way is to really not give you the VD, which is, so in that case it will be the default value. So here let's say not given, then VD is default 0.7 default. Okay, or he will give it to you, it will be given, and it will, in the question it will say VD is equal to blah blah blah. Okay, the third way for providing VD is if you see this kind of circuit. where you need to understand that you have VD in an indirect way. So VD here, it will be VO divided by number of diodes. The last way, which is the most trickiest, is that you are given this graph, okay, and VD will be written as a number in this at this side, and here it will be minus VZK. So it will be numbers. For example, here it will be 0.9 and here it will be minus 9 as an example. Okay, good. So let's move on. The next question says that we need to solve the same we need to repeat the exercises that we did in the previous video, but using non-ideal diodes rather than ideal diodes. Okay, let's do these first and then we'll do the rest. Okay, so as I mentioned earlier, in order to solve for I or V, you need to figure out the physical current. So the physical current is from high potential to low potential, so it's moving downwards. This is the physical, okay. So now diode is on, right? Diode is on. We need to replace the diode with what? A short voltage source. Sorry. Okay, so here we're having a voltage source and we need to find V here. I current. So V, the voltage drop V is being measured across the DC voltage source. So V is equal to 0.7. Okay. And I is equal to what? It's 5 minus 0.7 divided by 2.5K, which is equal to 1.72 milli. Let's take this step by step. Now, as we know that this is the ground, right? This is 0. And this is the positive polarity of the source, and this is the negative polarity of the source. Now, if you want to find this point, what you do is you move from the known side to the unknown side, meaning that you have to move from 0 and upwards to find the point here. Okay, so what you do is you say 0 and the sign that's far from you, which is plus, so 0 plus 0.7. So this voltage is 0.7. Okay, let's take another example. If I tell you that this is the unknown side, Vx, and this is 10, and the source is, let's say, 3. So we need to move from the known side to the unknown side. This is 10. The polarity that is far from you is minus. So 10 minus 3 will be 7. Okay. If you do it the opposite way, you have to say 7. The polarity that is far from you, 7 plus 3 will give you 10 again. Okay. I hope it's clear. This is a simple way of figuring out voltages across sources. Now, moving on to the next part. Here, the physical current is also from high potential to low physical. The diode is off because it's facing the current, the physical current. So, it will be represented as an open circuit. What's I here? I is 0 because we're having an open circuit, and V is equal to V plus minus V minus. Let's see. This is V minus, which is 0. This is V plus, which is equal to the following. Now we do not have current, so resistance is useless. The resistance is useless because we do not have a current. So this voltage, which is 5, is equivalent to this point, which is also 5. So it will be 5 minus 0, which is equal to 5 volt. Okay. Next part. Here we have high potential and low potential. So physical current is in this direction. Now, diode is also off. Okay. So we are going to represent it as a what? Short circuit. Open circuit. 2.5 kilo ohm, and here we're having minus 5 volt plus minus V and I. I is directly 0 because open circuit, and V is equal to V positive minus V negative. V positive is 0 and V negative is no current, so resistance is used. This is minus 5, this is minus 5 also, so to be 0 minus minus 5, which is equal to 5 volt. Okay, next part. So physical current is also in this direction, physical. Okay, diode is on, so it will be represented as a short circuit, voltage source. .5 kilo ohm minus 5 volt, and we're finding voltage drop across the source. Okay, so V is equal to what? It's equal to 0.7 because it's parallel to the DC source. I is equal to this point minus this point over the resistance. So what is this point? Now here it's 0, right? 0 minus the sign further from you is minus 0.7, so this point is minus 0.7. So here you're going to say minus 0.7 minus 5 divided by 2.5k, resulting in, let's see, minus 0.7 plus 5 divided by 2.5k is 1.72 milli. Okay, let's see the last two examples before we conclude. Okay, now this is an AND gate, and this is an no, I think we swapped them, right? This is OR gate and this is AND gate. In OR gate you always pick the largest voltage first. Okay, so this will be on and the rest will be off. When the diode becomes on, it will be converted to a voltage source because we are talking non-ideal here. Okay, 1 kilo ohm grounded, and this is V and this is I, 3 volt. If this is 3 volt, the sign that is further from you is minus 0.7, so here you will end up with 2.3 volt. So V is equal to 2.3 volt and I is equal to 2.3 minus 0 over 1k, which is 2.3 milliampere. Okay, doing this part now. For AND gate we pick the lowest voltage. This will be on, the rest will be off. Okay, now 5 volt, resistance 1k, and here we're having a voltage source. Now this is the positive polarity because this is anode, this is cathode. 1 volt. If this is 1 volt, the sign further from you is positive, and this is 0.7, so here you will end up with 1.7, right? Because 1 plus 0.7 is 1.7, and the current will be 5 minus 1.7 over 1k, which is equal to 5 minus 1.7 is 3.3 milliampere. Okay, now I think I will pause this video now, and in the next video we will talk about the small signal analysis. Okay, and then the further video we will speak on Zener diodes. Thank you for listening.